Welcome back. In this lesson, as we said, we are going to understand the importance of feature scaling and standardization, and we are going to use Stack Overflow to help us better understand why we need to scale data in KNN. Okay, so if we go here, you will see that this question was asked 3 years and 6 months ago, right? And it was viewed by 45,000 people. Okay, and the question says, could someone explain to me why you need to normalize data when using k nearest neighbors? I have tried to look this up, but I still can't seem to understand it. I found the following link, but in this explanation, I don't understand why a larger range in one of the features affect the predictions. Okay, so this is the question, and as we can see, we have 22 upvotes and we have 11 bookmarks. So as we can see, the top rated answer here is saying the k nearest neighbor algorithm relies on majority voting, right? And we know this by now, based on class membership of k nearest samples for a given test point. The nearness of samples is typically based on Euclidean distance, and we understand the difference between Euclidean distance and Manhattan distance, and when should we use each of them. Now, consider a simple two-class classification problem where a class 1 sample is chosen, black, along with its 10 nearest neighbors, filled green, right? So here we have, this is the query point or the test point, and the green points here are the k nearest neighbors or the 10 nearest neighbors, okay? In the first figure, data is not normalized, where in the second one it is. So this is data without normalization, and this is data with normalization. Okay, so as you can see, notice how without normalization, all the nearest neighbors are aligned in the direction of the axis with a smaller range, leading to incorrect classification. So if we look here, you will see that here we have two features, right? And without normalization, the range of x1 is from 0 to 3, right, or 4, while the range of x2 is from negative 15, right, to nearly 50, okay? So, without normalization, all the nearest neighbors are aligned in the direction of the axis with the smaller range, right? So here we have the 10 nearest neighbors are like this, right? So the data is not normalized well, so we have the 10 nearest neighbors not really representing the correct class, right? Because the data is not normalized. Now, if we perform normalization, as you can see, from negative 2 to 2 and from negative 2 to 2, now the query data, right, or the query point, now the 10 nearest neighbors, right, when we calculate them, we have one from red, right, and another one from red, and then here we have the other 8 from blue. So the class of this point will be blue, while here we could have the class of this point, the same point, right? This is the same test point, but here we will classify this point to be red, right, because the nearest neighbors here are mostly red, most of them are red, while here most of them are blue. And after normalization, we see that the actual distribution for the data shows that when we have a data point here, it should be blue, right? So this is very, very important, and this is the correct answer, and this answer is explaining it in a very, very good way, and you can check also the other answers. Okay, now let's go back. Now, in addition to what we have seen in the Stack Overflow question, you need to understand that k nearest neighbors is a lazy learner, right? What do you mean exactly by a lazy learner? It doesn't really learn anything, right? It's not like linear regression when we are learning parameters, right? It's a non-parametric model, so it's a lazy learner. So every feature is weighted equally in finding the nearest neighbor. So this feature will have the same weight as this feature. So if we have the range for this feature to be smaller than the range of this feature, then the weight for calculating the distance using this feature will be much smaller than the weight of this feature, right? So if all features are equally important, but they are not at the same scale, they must be normalized like this, right? Otherwise, the features with the largest magnitudes will dominate the total distance. Which distance? The Euclidean distance. We can solve this problem by using the Manhattan distance, right? As we said in the example in the last lesson, right? So I wanted to emphasize the importance of feature scaling and standardization, and especially in KNN. In the next lesson, we will understand a very important problem and a limitation for the KNN algorithm, which is a search space and the curse of dimensionality. So let's go.